1959. Europe recovers from World War II. Many eminent scientists have left for the United States. European research is no longer world class. To reconstruct European science, the visionary French physicist and Nobel Prize winner Louis de Broglie proposes the creation of a European laboratory that would be both a centre of excellence in physics and a motor for peace. His idea is taken up by American Nobel Prize winner Isidore Rabi, who together with Pierre Auger and Eduardo Amaldi convinced UNESCO to adopt this process. 18 months later, 12 European nations formally agreed to create the Conseil européen pour la recherche nucléaire. The acronym CERN is born. Important decisions are taken in the first sessions of the new council. Geneva is chosen as the seat because of its central location in Europe and its international tradition. Two accelerators are put forward, the Synchrocyclotron and a much larger machine, the proton synchrotron. A new convention defined CERN's goals, stating that its research will have no concern with military requirements and that all its results should be made public. The CERN Convention is signed by 12 nations. Among the signatories are eminent physicists such as Werner Heisenberg. CERN comes into existence. 1954. On a site in Mérin, a small village near Geneva, work for the new laboratory begins. Within a year, the farmland is transformed into a large complex of workshops, offices, and buildings to house the new accelerators. The 5-meter thick walls of the Synchrocyclotron building soon emerge, while the different parts of the new accelerators are manufactured in several European countries. The Synchrocyclotron's magnet coils require particular care to pass through some of the Swiss villages on their way to their home. As components arrive, they are assembled with great precision. Everything starts to take shape. The Synchrocyclotron emerges, piece by piece. Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the Synchrocyclotron is ready, and CERN's first accelerator comes to life. The purpose of the Synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light producing millions of new particles when those protons collide with a target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. Two D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after one half turn. Meanwhile, the radio frequency generator reverses the polarity between the two electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a half turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. In 1957, young scientists from all over Europe arrived. Among them are Maria and Giuseppe Pinicaro. Giuseppe wanted to study a short-lived particle called the pion. In 1957, there was a mystery surrounding the pion. Theory predicted that a direct decay into an electron and a neutrino should happen, but this had never been observed.
Phenomenology, only